Hello class, today we will be talking about how to use triangles, both isosceles and equilateral. Something to note, we're not going to be proving triangles congruent in this section necessarily, but we will be using different properties to note some things that I need to know. There is also two theorems in this section which you do need to know. Ironically, one of them will be abbreviated the A theorem. Base angles theorem, and then there's the converse of the base angles theorem. But anyway, moving on. The first concept you need to know is just the parts of an isosceles triangle. If we don't know what I'm talking about when I say legs of a triangle, it's going to be very hard to talk about isosceles triangle. Congruent sides of an isosceles triangle will be what we call the legs. So this side over here and this side over here will be the leg of my triangle because they're congruent. The non-congruent side is called the base. So this one, because it isn't congruent to the other two, is what I call the base. It doesn't mean it has to be on the bottom of my triangle, it just means it's the non-congruent side. So I could actually rotate this, and my base could be over here. The angle opposite the base is called the vertex. So if this is the base, this angle up here has to be the vertex. It's across the shape from the base. Then the angles adjacent to the base are called the base angle. So this angle here and this angle over here are what we call a base angle. There is something unique about the base angle and the legs, but right now I'm going to ask you to simply just identify the parts of a triangle, or what are the parts of this triangle. I've labeled these angles as A, B, and C, and these sides as A, lowercase b, and lowercase c. So A is the / blank. Go ahead and try this real quickly. Alright, you should have got A here to be this lowercase a, to be the base. So A is the base. B ends up being a leg, so B is a leg. C is a leg. Capital A here is an angle, and seeing it's across from the base, I'm going to say it's the vertex. A is the vertex. Capital B over here is across from the leg. It's also adjacent to the base, so it's going to be a base angle. B is a base angle. And last but not least, C here, because it's adjacent to the base, C is a base angle. These are the parts of a triangle. You have to be able to identify them. If you're not, review this. Concept 20, the base angles and the legs of an isosceles triangle. They are related. One says if two sides of a triangle are congruent, then the angles opposite them are congruent, also known as the base angles are congruent. So if I have two legs being congruent, I have the base angles being congruent. Converse of the base angles theorem, if two angles of a triangle are congruent, then the sides opposite them are congruent. So if I have the base angles being congruent, the legs have to be. So if I look at this picture, if I saw these two angles being congruent, I would know that these two sides have to be, because they're opposite of those angles. This side is opposite this angle. This side is opposite this angle. Have to be congruent. If I got these two sides to be congruent, these two angles have to be congruent. With these two theorems, we have a two-way street. Base angles theorem, one way to remember that that's the one that says the base angles are congruent is because it's the base angles theorem. It's about the base angles. We want to know something about the base angles. The converse of the base angle theorem means that we already know something about the base angle theorem. And now we're going to be saying something about its legs. So, if I have two sides in a triangle being congruent, I have at least two angles, the base angles being congruent. If I have two angles in a triangle being congruent, I know I have at least two sides being congruent. This is a relationship that's always true. The next example using the base angle is just to find the value of x in each problem. So go ahead and try and do these now. Alright, I would strongly suggest you copying down this yourself, just so that way you can see them. I'm going to write in red the answers to these problems. if I look at the first one here, I see that I have this side and this side being congruent. That being said, that tells me then that this angle here and this angle here have to be congruent. And if those two angles are congruent, that means their measures are equal. So 5x is equal to 65. They have to be. And at this point, all I do is solve for x. Divide both sides by 5, I get 13. That one's done. Number 2 is a little bit tougher. However, it's not that bad. If I look here, these two sides are congruent, which tells me these two angles are. If these two angles are congruent, I know that that one has to be 45 degrees. And if I know these two, and I know this one here, well, all the angles of a triangle have to add up to be, 180. So what I have here would be 45 degrees plus 45 degrees plus 5x degrees equals 180 degrees. Simplify as far as I can. 90 degrees plus 5x degrees equals 180 degrees. Subtract 90 degrees from both sides. Divide both sides by 5, and I'm going to end up getting 18. X is 18. Number 3 over here, it's actually pretty straightforward. If I have these two angles being congruent, that means these two sides are congruent. X is 15. And the last one, if I look at the picture, it looks like this, 6 meters and 3x meters. Well, again, these two angles are congruent, so that means these two sides across from them are congruent. So 6 equals 3x. Divide both sides by 3, I get 2 equals x. And that's all there is to this part, really. It's using the base angle theorem and then setting it up. You're generally going to get equals set equal to each other, but there is a case where you're going to have to add them all up to be 180, and that's when you're looking for the vertex or you're given the vertex. And there we go. This is some examples of the base angle theorem. Example 3. Oh, there is not an example 3. The next concept we'll talk about is equilateral and equiangular. If we look quickly back at this concept, it said if two sides of a triangle are congruent, then the angles opposite them are congruent. It happens that if I have sides being congruent, the angles opposite them in a triangle will always be congruent. The angle across and the side across always match up. If I have the largest side, it actually matches up to the largest angle. If I have the smallest side, it actually matches up to the smallest angle. I know right now all we're doing is worrying about if they're equal or they're congruent. But it ends up being that the side across matches up perfectly. Not necessarily in number, but if it's the largest, it's going to be the largest. Largest angle matches up to the longest side. It's always true in a triangle. So if I have the same side for all three, then I have to have the same angle for all three. If I have the same side for two of them, I have to have the same angle for two of them. The corollary here just says if a triangle is equilateral, then it has to be equiangular. If I have three sides being congruent, then the three angles have to be. And the converse, the corollary to the converse of the base angles theorem says if I have it being equiangular, it has to be equilateral. So this goes either way. If it's one or the other, like equilateral or equiangular, then it also has to be the other. If it's one, it's both. So let's look at a few examples. Example 3, find the value of x and y. For the first one here, I'm not even going to put it on the backboard. This here, I have three congruent angles, so this triangle is equiangular. If I look back, if equiangular, right here, then equilateral. So this is equilateral. All the sides are the same length. So x has to be 5, y has to be 5. Pretty straightforward. Not a whole lot of work to show here. X is 5, y is 5. Done. Moving on to 2. Alright, 2 and 3 I'm going to put on the backboard. Alright, for number 2 up here, I look, it's equilateral. I have 3 sides being marked congruent. So therefore, these 3 angles are also congruent. If those 3 angles are congruent, that means they're all the same angle. That means this is 6x degrees here. That means this is 6x degrees here. So what I have is 3 6x degree angles. And I know from the triangle sum theorem that if I add all 3 of them together, I'm going to get 6x plus 6x plus 6x equals 180. Add them together. I get 18x to equal 180, and I get x to be 10. One thing to note, the angle, if it's equal angular, will always be 60 degrees. I probably could have done a shortcut here and said 6x equals 60, because if it's equal angular, every angle is 60 degrees. And I could have just then said x is 10. But if you did it this way, that's entirely fine. In fact, this way will always be right. For number 3, again, I look. Well, I have to choose which triangle to start with. My preference would be to start with this triangle here. I see it's equal angular, so I know it is equilateral. I also realized I forgot to put a length in over here, 16. Now, I only put 1 mark here. I could have really done 2 here, and why not? Let's do it. 2 marks each. Wait. If this is 16, this length is 16. If this length is 16, all of these are 16. So what this is saying is, because this is 16 all the way over here, x also has to be 16. Okay? For the next part, I realize y is over here. It's talking about angles. I look real quickly. Do I see anything like a right angle or a straight angle? The answer is no. So what I'm going to do is I'm going to erase the part of the triangle I no longer need. There was nothing over here that could help me, so I erased it. I'm also going to erase the lengths, because if y is an angle, there's no way I know how right now to get that angle measure using lengths. So why would I keep it in my problem? If I look, these 2 sides are congruent, which means these 2 angles are congruent, which means this is also a y. If I look, just like I did up here, all the angles of a triangle have to add up to be 180. So I'm going to do y plus 18 equals 180. Solve for y, I get 2y plus 18 equals 180. Subtract 18 from both sides, I get 162. Divide both sides by 2, and I get 81. So x in this case is 16, y ends up being 81, and there we go. This is using both the base angles theorem and the corollaries of the base angles theorem, equal angular and equilateral. I think that's all I have for this time. Till next time.